addition of halide to aldehydes or ketones. The phytic reaction. A general reaction is summarized by the shown equation. Aldehyde or ketone plus phosphorus halide gives alkene as Z and E isomer زائد plus triphenyl phosphine oxide. This reaction have many advantages over the previous method of alkene synthesis. First, there is no doubt in the location of the double bond in the product alkene compared to the possible formation of different alkene by E1 reaction because of carbocation rearrangement, and also this reaction is advantageous over the E2 elimination method for preparing alkene, because in E2 method there is many possibilities for eliminating beta proton to form the double bond. The synthesis involve two reactions. The synthesis of halide involves two reactions. SN2 reaction between triphenylphosphine, commercially available reagent, and alkyl halides to give the alkyl triphenylphosphonium halide salt. Action 2, deprotonation of the acidic proton of the alkyl triphenylphosphonium halide with a strong base, for example alkyl lithium, to form the halide, phosphorus halide. Halide can be represented as a hybrid of two resonance structures. By quantum mechanics, it was proven that the second structure is more important. This halide can then react with carbonyl group of aldehyde or ketone as the following. Halide react in a cycloaddition reaction, concerted cycloaddition reaction with aldehyde or ketone to form the 4-membered ring intermediate oxaphosphetane, which unstable and decomposed to alkene as E and Z diastereomer, and triphenylphosphine oxide acid product. Note that E and Z isomer here results from attack of the lead, from the action of the lead on both sides of the carbonyl group. On the right side, as illustrated in the scheme, attack of the interaction of the lead can take place from the right side or from the left side of the double bond. Remember that the carbonium, the CO double bond is planar structure, and all the 3 groups around the involved in the structure are in one plane. Carbon here is sp2 hybridized. All the 3 bonds are in one plane. Specific example: cyclohexanone زائد methylate give the alkene methylene cyclohexane in very good yield. The methylate is prepared from methyl triphenylphosphonium bromide and butyl lithium, and then react with cyclohexanone. The driving force in phytic reaction is the stability of triphenylphosphine oxide, because the phosphorus oxygen double bond is a very strong bond. This compound is a very stable compound, and formation of phosphorus oxygen double bond is the driving force for this reaction. This equation summarizes the overall result of phytic synthesis. The first step gives the alkene. Remember that the alkene emerged, formed as to E and Z isomer. Advantages of fatigue reaction. As we mentioned before, the advantage of fatigue reaction includes: first, applicable to a wide variety of compounds, including aldehyde and ketones. The product is an alkene with the double bond in the desired position, even it is not the most stable alkene. This is great advantages compared to E1 method for preparation of alkene. Yields are generally good for mono, di, and tri-substituted alkene. Number 4, this synthesis is very practical. Most of the steps can be carried out in the same reaction vessel. It's called one-pot reaction or one-pot synthesis. This method is a one-pot synthesis. The entire synthesis can be accomplished in hours. Planning fatigue synthesis. We can illustrate this process by the following example. We examine the structure of the desired alkene and pay attention to the both group on every side of the double bond. We give attention, we pay attention to the grouped on the both sides of the double bond. 2, choose the alkyl halide to make from it the yield and choose the ketone or aldehyde. In this example, we can consider 2 pathways. In what is so-called retrosynthetic analysis. Here we say that this double bond can be formed from this yield and benzaldehyde. Then we consider this yield can be prepared from the secondary alkyl halide to bromo or to chloropropan زائد ترايفينايل فوسفين. The second strategy, we use the acetone and the yield produced from benzyl triphenylphosphonium salt, which can be prepared from benzyl halide and triphenylphosphine. That is the analysis to identify our starting for the synthesis. Consider the strategy A, then we can write the synthesis as follows. 2-bromo-propan plus triphenylphosphine give phosphonium salt as propyl, triphenylphosphonium bromide. We can prepare the arid by using of potassium, by using of alkyl lithium to form the negative charge. This arid will react with benzaldehyde to form the required product. Following the retrosynthetic analysis or strategy B, we make the arid from benzyl halide and allow it to react with acetone as follows. Triphenylphosphine plus benzyl bromide gives benzyl triphosphaneum bromide. The proton can be abstracted, can be removed by alkyl lithium to give the arid. Arid react with acetone to give the required product. Modifications of heating reaction. We can use a phosphonate ester in place of sulfonium salt to carry out modified heating reaction. Phosphonium ester has acidic proton. The proton attached to phosphorus atom. We can abstract this proton with strong base such as sodium hydride or alkyl lithium to form the carbanion. This carbanion take the place of yield in phytic reaction. Thus, we add aldehyde or ketone to the produced carbocation to obtain alkene. in a similar mechanism as in Wittig reaction. The advantage of this method is the formation of alkene as mainly E isomer. The E diastereomer will obtained as major product. Reaction of aldehyde and ketone with sulfur yalides. Sulfur yalides, like phosphorus yalides, contain carbanion attached to positive sulfur atom. We can prepare sulfonium yalide by abstraction of proton from sulfonium salt with strong base, such as sodium hydride. For example, potassium trimethyl sulfonium iodide can be converted to yalide, sulfur yalide, with sodium hydride in dimethyl sulfoxide. Reaction of sulfonium yalide with aldehyde or ketone brings about the oxyron in two steps. First step, the addition to the carbon to form the alkoxide, and then internal SN2 reaction to form the oxyron and dimethyl sulfide. This is a good method for preparing the oxyron because it is a general method applied to different types of aldehyde and ketones, and the product obtained in very good yield. Oxyron are a very important synthetic intermediate in organic synthesis and find many applications. A review problem. Triphenylphosphine can be used to convert epoxide to alkenes. For example, the shown equation. Propose the likely mechanism for this reaction. The case step in solving this problem is the oxyron ring cleavage by the strong nucleophile triphenylphosphine. That's to say, SN2 reaction between the strong nucleophile triphenylphosphine and the oxyranging add benzylic carbon to give the four-membered ring oxaphosphetane, like what's happening in phytic reaction. Oxaphosphetane decomposes to alkene with the formation of triphenylphosphine oxide. Oxidation of aldehydes. Aldehydes are easily oxidized with strong oxidizing agent such as potassium permanganate in alkaline medium, or by weak oxidizing agent as silver oxide in alkaline medium, to give the carboxylate, corresponding carboxylate, which can be acidified to give the corresponding carboxylic acid. You remember that in the lab work you have carried out the oxidation reaction for the aldehyde groups by Tollens reagent to observe the formation of sulfur mirror on the inner side of the test tube. Samples of aldehydes are slowly oxidized by oxygen in the air. Therefore, aldehyde samples contain carboxylic acid, the corresponding carboxylic acid as impurities. Additional problems. Predict the major products from each of the following reactions. I will give some spot lines for solving some of this problem. First problem is ethyl formate with this granular reagent followed by hydrolysis and treatment with chromic acid. First reaction, the addition of granular reagent to the carbonyl group of the ester to give unstable product which decompose to give the aldehyde and liberate magnesium alkoxide. This aldehyde is much reactive than the original ester, so that it will react immediately with excess reagent to form, after acid hydrolysis, the secondary alcohol. Here, hydrolysis is carried out in acid medium, as you show. This acid medium hydrolyze the acetal in the reagent, in the structure of the reagent, give the corresponding ketone. The final reaction is oxidation of the secondary alcohol with chromic acid. This is a standard method for preparing alcohol. Thus, the final product should be andecan 2,6,10 trione. That is a symmetric ketone. You should work on solving this problem written. Again, you should work on solving each problem of this problem written. The last problem is addition of cyanohydrin to this aldehyde. Addition of hydrocyanic acid to the aldehyde group gives cyanohydrin, corresponding cyanohydrin. Cyanohydrin is reduced by lithium aluminum hydride in the second reaction, followed by hydrolysis, of course. Followed by acidification. Second reaction is reduction of the aldehyde with lithium aluminum hydride, followed by acidification to liberate the alcohol. Another set of additional problems. You have benzyl bromide. Show how you would synthesize each of the following. First problem is an alcohol. We followed here the retrosynthetic analysis. That is to say, from backward of the end product to the starting material. So we consider that this alcohol, which can be obtained from ketone. This ketone can be obtained from benzyl cyanide or benzyl nitrile by treatment with methyl magnesium bromide followed by hydrolysis. This is a standard method for preparing ketone from nitrile. Then benzyl nitrile can be easily obtained from benzyl bromide by treatment with sodium cyanide or potassium cyanide in SN2 reaction. Again, you should work on the solution by rewrite the synthesis from the starting. Thus, benzyl bromide plus potassium cyanide SN2 reaction give benzyl nitrile. Benzyl nitrile will be treated with magnesium with Grignard reagent, which is methyl magnesium bromide followed by acid hydrolysis. Give the ketone, which is named 3-phenyl-2-propanone. The name of this ketone, the resulting ketone, 3-phenyl-2-propanone. This ketone can be reduced with lithium aluminum hydride followed by acidification to give the corresponding secondary alcohol. This is the first problem. The second problem here, we know that the side chain contains 3 carbon atoms. Problem number B. The side chain, including the aldehyde group, contains 3 carbon atoms, and our starting product, our starting material, contain 1 carbon atom. Therefore, we must use reaction which brings further 2 carbon atoms. We consider that also in retrosynthetic pathway, retrosynthetic analysis. We consider that this aldehyde can be obtained from the corresponding alcohol, that is, which is 3-phenylpropanol. This alcohol can be obtained from benzyl magnesium bromide and treated with oxyran. Again, this alcohol can be obtained by reaction of benzyl magnesium bromide, granular reagent, with oxyran. Note that we chose oxyran because we added 2 further carbon atoms in the side chain. Granular reagent can be obtained here from benzyl bromide and magnesium ether. So we write the synthesis in the normal way, starting with benzyl bromide plus magnesium ether with benzyl magnesium bromide, granular reagent plus oxyran, and followed by acidification, give 3-phenylpropanol, which it can be oxidized very easily with pyridinium chlorochromate to give the corresponding aldehyde. Also, you should work on the solution by rewrite these steps. In this slide, a scheme including some synthetic transformations of the subjects we have studied, including the preparation of aldehyde and ketones and reactions, aldehyde and ketones. You should work on each transformation to know or to remember the experimental condition and advantage and disadvantage of these transformations. Another important feature of aldehyde and ketone is that the alpha hydrogen are weakly acidic. They are weak. We say that they are weak acids. They are weaker than another organic acid, for example, alcohol and thiols and sulfonic acid or carboxylic acid. But they are stronger acids than other type of hydrogen. For example, hydrogen in ethane, pKa 25, hydrogen in ethene 44, hydrogen in alkane about 50. Well, remember that the pKa for aldehyde, for alpha hydrogen in aldehyde and ketone about 20. This acidity can explain as follows. When a proton is abstracted from the alpha hydrogen, the carbanion formed called enolate is stabilized by accommodation of the negative charge on the oxygen. The resonance hybrid represent the stability of this type of carbanion. Here is shown the representation of the resonance hybrid carbon carry negative charge, partial negative charge. Oxygen carries partial negative charge. The contribution of the resonance structure in which oxygen bear full negative charge is more important because the oxygen atom can accommodate negative charge better than carbon. Abstraction of proton from the alpha hydrogen results in enolate. Only enolate can accept proton at either carbon or oxygen. When enolate accepts proton at carbon, we obtain the starting ketone. When it accepts proton for oxygen, we obtain form which has H on the oxygen on the double bond, the carbon. This form is called enol form. Both the formation of the keto form and the enol form from enolate are reversible. Two reversible reactions. In other words, there is equilibrium between keto form and enol form through the formation of enolate. This transformation, called tautomerization, and keto form and enol form, which are structural isomer, we call tautomer. The process called tautomerization. Formation of enolate brings about some important reaction we study in the following slides. When a solution of optically active chiral ketone is treated with dilute acid or dilute base, the solution after some time loses its optical activity. The optical activity will be lost. That's to say, the compound, the ketone transformed into two equal amount of the enantiomer. That is what's called racemization. We can explain the racemization by formation of enolate in base medium, by formation of enol by enolate in basic medium, or formation of enol directly in acid medium, as follows. again, we can account for the racemization through the formation of enol by enolate in basic medium, or formation of enol directly in acid medium, as the following slides indicate. Base catalyzed enolization, which brings about racemization. Base abstract proton from the ketone to form enolate. Enolate is a planar structure, a chiral structure. Enolate abstract proton from water to form enol. When enol referred to the ketone through reversible reaction, it accepts proton at either faces of the planar structure. Enol refers to enol plus proton to form enolate. Enolate planar structure which accept proton from upper face on the lower face and transform to racemic mixture of the chiral ketone. This is base catalyzed enolization. Acid catalyzed enolization is indicated here. Ketone abstract proton from the acid medium, from hydronium ion, to form enol. Enol, we repeat again, a chiral structure, planar structure. When it accepts proton from the hydronium ion, it accepts proton from upper face, from the top face, or from the bottom face, to form racemic mixture of the starting chiral ketone.